So we've talked about how to decide whether a molecule is polar or not. And now we want to relate molecule polarity to the types of intermolecular forces that act between molecules. So what is an intermolecular force? An intermolecular force is different than a covalent bond and rather different than an ionic bond in a lot of ways. The first thing to think about is that intermolecular forces don't act to hold atoms in a molecule together. They act between molecules to keep molecules close to one another. And so the reason we're talking about it at this point is we're discussing phase changes and phase transitions. When you turn a solid into a liquid, you're disrupting intermolecular forces, those attractive forces between molecules. And what are those intermolecular forces? Well, the surface of molecules you can think of as being kind of coated with a slippery and always moving film of electrons. Electrons have a negative charge. So in many ways, what molecules are coated with is like a slimy surface of negative moving charge. But molecules only have so many electrons. We know kind of from basic physics and how electric current moves and electrons interact with one another that through Coulomb's law, opposite charges attract and like charges repel. So if you have two positive charges, they push each other apart. You can think of that as two atomic nuclei. The nuclei of atoms would push each other apart if electrons didn't hold them together in covalent bonds, which are intramolecular forces, bonds inside of a molecule. Electrons tend to push each other apart. That's why for two electrons to occupy the same orbital, they have to have opposite spins, which gives them complementary magnetic attractions and keeps them in the same orbital. So if you think about it, when electrons encounter other electrons, they tend to repel one another. And so if you looked at it solely from that standpoint, if molecules are just coated with kind of a uniform film of electrons, molecules would always repel each other and they would never be able to get close enough except at very, very cold temperatures to form liquids or solids or more condensed phases of matter. But electrons are in constant motion. They have quantum properties. They're kind of everywhere and nowhere in the molecule all at the same time. Based on polarity and our electron density maps, we can say where electrons are more likely to be in a molecule. Electrons, both lone pairs and bonded electrons, are likely to be closer to electronegative atoms inside a molecule. And what that means is you have regions on the surface of the molecule where you have a higher density of electrons, leading to a buildup of relatively negative charge, and you have regions where electrons are not likely to be, which exposes kind of the nuclei of the atoms in that part of the molecule and leads to regions of buildup of positive charge. And so the intermolecular forces that act between molecules comes from these localized regions of positive charge and localized regions of negative charge attracting each other. And so the number one thing I want you to take away because of that, what that means is polar molecules, where you have these buildup regions of negative charge and positive charge, more electrons, less electrons, have stronger intermolecular forces. Because all intermolecular forces are kind of a manifestation of Coulomb's law, which says that opposite charges attract, like charges repel. So the more polar a molecule is, the more likely it is to have more electron density here, less electron density here, and you have regions of partial positive and partial negative charge. If they line up between molecules, you end up with an attractive force where the more electron poor region of one molecule is attracted to the more electron rich region of another molecule, pulling them together. The strength of the intermolecular forces then is related to the polarity of the molecule. We're going to see that more polar molecules have more different types of intermolecular interactions and stronger intermolecular interactions than nonpolar molecules. And it's the strength of these intermolecular forces that determine the physical properties of the molecule, like the boiling point and the melting point of the molecule. The more polar the molecules, the stronger their intermolecular forces tend to be, the higher their melting and boiling points tend to be. For example, and it's worth noting that the size of the molecule also counts. So if intermolecular forces have similar strengths, if you're looking at two different molecules and trying to make predictions about them, if two molecules have similar intermolecular forces but different molecular weights, the size of the molecule counts for something as well, and generally larger molecules have higher melting and boiling points given similar intermolecular forces. So let's take a look at what that means. Here are two molecules that are kind of similar. Dinitrogen, which we've decided is a nonpolar molecule, no dipole moment across the bond. Homonuclear diatomic molecule has no dipole moment. Ammonia is a polar molecule, trigonal pyramidal molecule. Electron density is kind of up here on top of the nitrogen where the lone pair is in the Lewis structure. It's a polar molecule. Their molecular weights are not that dissimilar. They're not identical, but they're not that dissimilar. Dinitrogen is strictly a gas at room temperature. Being a nonpolar molecule, its intermolecular forces are very weak, and its melting point is around negative 210 degrees Celsius, and its boiling point is only a little bit higher than that at negative 195 degrees Celsius. Even though it's a similar size molecule, ammonia has stronger intermolecular forces acting between the molecules. Being a polar molecule, its melting point is still not impressively high. It melts and forms a liquid at about minus negative 78 Celsius and has a boiling point of minus 33 degrees Celsius, so tends to be a gas at room temperature. What we want to do here first and foremost is introduce you to the types of intermolecular forces that act to attract molecules together and tell you about which intermolecular forces nonpolar molecules possess and which intermolecular forces polar molecules possess. Bearing in mind that the punchline is the more polar the molecule, the more types of intermolecular forces are likely to exist between the molecules and the more strongly they're going to be held together. Remember, the bottom line is that intermolecular forces are based on electrostatics. What pulls molecules together are temporary or permanent, in some cases, buildup of partial negative and partial positive charge. And remember that opposite charges attract. So regions of partial positive charge on one molecule find regions of negative charge on another molecule, and that creates an intermolecular force that holds the two molecules together. Polar molecules have stronger intermolecular forces because they have more permanent and localized regions of electron density and electron pore regions on their surface. Nonpolar molecules have kind of uniform electron density, and as a result, their intermolecular forces are pretty weak. There are four types of intermolecular forces, which are sometimes referred to generally as van der Waals forces, after the same physicist, physical chemist, who made those modifications to the ideal gas law to better reflect the behavior of real gases that we talked about at the end of chapter 8. And the four classes of intermolecular forces are dispersion forces, which are the weakest, dipole-dipole forces, which are a little stronger, hydrogen bonding, a little stronger still, and ion dipole forces. Of these four, only the lower three, hydrogen bonding, dipole-dipole forces, and dispersion forces, are present in pure compounds. Ion dipole forces only act when you have mixtures of solutions and you have combinations of ions and covalent molecules. So when we're talking about assigning intermolecular forces to covalent molecules, we're really only going to consider the lower three. Ion dipole forces only act in very large molecules like the proteins in your body that meet specific criteria. Otherwise, they're only for mixtures of chemicals that contain both ionic compounds and polar covalent compounds. So we're going to talk about all these types of molecular forces, but we're really going to focus on the lower three. And the idea is that dispersion forces are the weakest, dipole-dipole forces a little stronger, hydrogen bonding a little bit stronger still, ion dipole forces tend to be the strongest. As a result, what we're going to see is because the polar molecules have access to the stronger intermolecular forces, the more polar your molecule is, the more likely that it will be able to access one of these intermolecular forces that's stronger. Non-polar molecules only have dispersion forces acting between them, and that's as a result, their intermolecular forces are quite weak. That makes their boiling points low, their melting points low, etc. The other thing to keep in mind is that molecules can possess any or all of these forces depending on their structure and polarity. The more polar they are, the more likely they're going to be able to access one of these, or the more likely they are to be able to access the strongest of these three intermolecular forces, which is hydrogen bonding. But even polar molecules that can hydrogen bond also have dipole-dipole forces and dispersion forces. So it's kind of like collecting cards in your hand to play a better poker hand. The more polar you are, the more of these types of intermolecular forces you get to claim. So if you're a polar molecule, not only do you have dispersion forces, not only do you have dipole-dipole forces, but maybe you can also hydrogen bond. And the more of these you have access to, the more tightly held, the more strongly attracted to each other the molecules in a chemical sample become. So another way of saying that is dispersion forces act in all molecules and even monatomic gases like noble gases. No matter how nonpolar you are, you at least have dispersion forces acting between your molecules. If you're a polar molecule, you at least have some type of dipole-dipole force in addition to the dispersion forces. So if you're a polar molecule, you have both this and this. Certain polar molecules that are very polar, or another way of looking at it as they have a specific structural motif as part of their molecular geometry, can also hydrogen bond. So certain polar molecules can hydrogen bond. But if you can hydrogen bond, by definition, you can also interact through dipole-dipole forces and dispersion forces. So the more polar a molecule, the more of these three key intermolecular forces you can lay claim to. Again, ion dipole forces act primarily in mixtures of chemical compounds where you have something like a solution of an ionic compound like sodium chloride dissolved in water. So we will talk about ion dipole forces, but in general, when we talk about intermolecular forces, we're talking about the lower three: hydrogen bonding, dipole-dipole forces, and dispersion forces. All right, so remember that all intermolecular forces are based on attractions between regions of partial negative and positive charge in molecules. We're going to start by describing dipole-dipole interactions because I think they give you the cleanest picture to visualize how these intermolecular attractions work in any type of molecule, even though dipole-dipole interactions are only present in polar molecules, not nonpolar molecules. So dipole-dipole interactions are electrostatic, that means positive negative charge attractions between two polar molecules. And even though there is no true +1, -1 kind of charge in a polar molecule, if you have a polar molecule like this iodine chloride molecule here, you have a region of positive charge where the less electronegative atom is, and you have a region of localized negative charge, more electron density, where the more electronegative element is. And so as a result, the bond dipole in the iodine chlorine single bond points towards the chlorine, and that bond dipole is the same as the molecule's dipole because it's a heteronuclear diatomic. So if we modeled it as a cartoon, green ball is our iodine, gray ball is our chloride. Here's our region of partial positive charge, it's where the iodine is. Here's our region of partial negative charge. The chlorine has gotten more of the electron density because it's more electronegative. If these iodochlorine molecules line up so that one of the chlorines is facing one of the iodines, you get an attraction between the two because you have partial negative, partial positive. Even opposite charges attract, and even partial opposite charges attract. So even though you only have kind of relatively negative charge here because of the buildup of electrons and relatively positive charge here, still there's an attraction there. And that's what your dipole-dipole interaction is. So when your molecules line up in a certain way, either head to tail like this, or flip-flopped and stacked on top of each other like that, you have attractive forces between the regions of relatively positive charge and relatively negative charge on the molecule. Electron poor region, electron rich region attract each other. And this is the fundamental type of interaction that kind of all intermolecular forces are based on. It's just most obvious in the dipole-dipole interactions. So polar molecules can access dipole-dipole interactions, and dipole-dipole interactions, though, are a good example of what intermolecular forces really are. Regions of electron poor and electron rich areas of two molecules being attracted to each other because partial opposite charges still attract. But what about nonpolar molecules? How can nonpolar molecules, which have uniform electron density, be attracted to one another? Well, electrons are in constant motion. They're quantum, right? Everywhere and kind of nowhere in the molecule at the same time. Another way to think of that is they're in constant motion around the molecule. So if electrons are in constant motion around the molecule, if you have a nonpolar molecule, there must be short, tiny slices of time where the electron density is not perfectly uniform, even though neither of the elements are more electronegative. So another way of saying that is we would expect on paper something like dihydrogen to have perfectly uniform electron density because there's no bond dipole. And as a result, two hydrogen atoms, in that case, or two hydrogen molecules, H2 and H2, should repel each other because they're kind of perfectly coated with electrons. Those like charges should repel. But even in a nonpolar molecule like dihydrogen, those electrons being in constant motion, at some point, only two electrons in this whole molecule, sometimes for a very small segment of time, the electrons are over here, not over here, or they're over here, not over here, or they're between the atoms rather than on the outsides of the atoms. And this leads to very temporary regions of electron poor and electron rich surface in the molecule. And that still gets you a weak attractive force that even nonpolar molecules have access to. So even the least polar of molecules still can access these what are known as dispersion or London forces or induced dipole forces, where as the molecules, particularly as the molecules move together, their electron clouds may squish a little bit, and you actually end up with, for a brief amount of time, a region of electron poor surface area in one molecule and electron rich surface area in the other molecule, and you get a very weak temporary attraction. That's a dispersion force. It's like a very, very, very short-lived dipole. It's a very weak relative of that dipole-dipole interaction. The third type of intermolecular force that we commonly encounter is what's known as a hydrogen bond. And only very polar molecules with a specific structural feature can hydrogen bond. A hydrogen bond is like a very strong dipole-dipole interaction that involves two atoms and a lone pair. So for a polar molecule to be capable of hydrogen bonding, which is generally the strongest of our three basic types of intermolecular forces, hydrogen bonds can only occur between very polar molecules which possess a hydrogen atom that has a covalent bond to a very electronegative atom, nitrogen, oxygen, or fluorine, that also has a lone pair on it. So for a polar molecule to be able to hydrogen bond, we need a hydrogen bound to one of the most electronegative atoms on the periodic table. And oh, by the way, that electronegative element also has to have a lone pair on it. So all those criteria have to be met. Water is capable of hydrogen bonding, for instance, because we have a hydrogen covalently bound to this oxygen atom. That oxygen atom has a lone pair on it. So this is a polar molecule that can also hydrogen bond. And what a hydrogen bond is just an extreme example of a dipole-dipole interaction where this molecule has become so polar and the electron density difference has become so great between the hydrogens and the lone pairs on the other side of this oxygen atom that the lone pairs on this oxygen atom start making a strong attraction to the hydrogen on an adjacent atom. Just a very extreme case of dipole-dipole interactions, and many of your covalent compounds that have very high boiling and melting points are hydrogen bonders. So water is a great example of that. Despite being a very light molecule, a molecule with a low molar mass, water, because it is a polar molecule that can hydrogen bond and has the geometry actually to form a very strong hydrogen bonding network throughout either solid or liquid water, has very high melting points and very high boiling points for a molecule of its size. So these are your three types of intermolecular forces. London forces, also known as dispersion forces, are the weakest. Dipole-dipole forces are a little stronger. Hydrogen bonds are a little stronger still. Nonpolar molecules have dispersion forces. Polar molecules have dipole-dipole and dispersion forces. Very polar molecules, where you have a hydrogen attached to oxygen, nitrogen, or fluorine, also containing a lone pair, are hydrogen bonding molecules. And water, for instance, has the full suite of intermolecular forces: hydrogen bonding, dipole-dipole, and dispersion forces all acting between molecules, which allows the water molecules to be held together very strongly, giving the water high melting point and high boiling point. Last but not least, for mixtures of chemical compounds like sodium chloride dissolved in water, you can also see ion dipole interactions. And these are electrostatic interactions that occur between a charged species like a cation or an anion and the electropositive or the electronegative regions of a water molecule. So if you look at an ion like sodium, when you dissolve sodium chloride in water, it splits up into sodium plus 1 and chloride, Cl minus. Sodium plus 1 is a cation, positive charge. It would be attracted to that electron-rich region of water, which is the oxygen with the lone pair. And so water molecules tend to line up around that sodium atom with their oxygens facing it, giving this a sort of really strong dipole interaction. So it's a particularly strong case of dipole attraction between the water molecule and the sodium ion. This is an ion dipole interaction. The same would happen for chloride ions dissolved in water, where the negative chloride would have water molecules lining up with these electropositive hydrogen tails around the chloride. And so ion dipole interactions are generally the strongest type of intermolecular force that acts in very large molecules that have ionic character to them, like proteins or nucleic acids, and also acts when you have solutions of ionic compounds dissolved in polar covalent solvents, polar protic solvents like water. So ion dipole interactions are our last type of intermolecular attraction. However, they're really only applicable in our case in solutions of ionic compounds dissolved in water. So we're not going to talk about them too much. And for the most part, we're not going to deal with any small molecules that have the opportunity to have ion dipole interactions between them. So if you're asked to assign intermolecular forces to a pure sample of a specific chemical, your only options are going to be hydrogen bonding, dipole-dipole, and dispersion forces, and you make assignments based on the polarity and the structure of the molecule. And that is what we're going to try in our first practice example today. So in the example coming up, I'm going to ask you to apply what we've learned about the polarity of molecules and what we've learned today about the type of intermolecular forces that polar and nonpolar molecules have. And I'm going to ask you to look at 5 molecules and tell me what type of intermolecular forces they have. So at this point, we're going to end this video, hop on over to the next page, and I'd like you to do a little spade work before we get into this example. You'll find your instructions on the next Canvas page. See you there.